What's up, everyone? It's Miss Nielsen, and we are talking about the AP Physics 1 summer assignments because I have a feeling that even though there's less than a week until school starts, not a lot of you have started it. So we're going to talk about it today in anticipation of the many questions that we will get within the next week. Hopefully you've gotten to take a look at this first page and you know that myself and Mr. Andringa teach this class. Our emails are linked there. Please reach out with any questions that you have, but hopefully this video covers a lot of your questions. Hopefully you also know who you have first semester. So this summer assignment, the actual assignment has two parts, the math and vector practice, which is the packet that you have, and then this second part called laboratory design, which is an extra little thing that is not attached to the packet, but we don't want people to forget about it. We will talk about that at the end of this video. You have to design an experiment and do some stuff. It's not too long, don't worry, but don't forget about it. If you have questions, go to the end of the video, okay? Hopefully, again, you got a chance to at least look over this packet, especially that first page. We are collecting this on the first day of school. To kind of help you get jump started, there are some really good resources listed on this second page. LearnAPPhysics.com is a wonderful website. It's got so many great videos, and we're going to use it sometimes in class, but it's a good thing to bookmark. It's a good thing to use because it's got a lot of multiple choice practice banks as well, which are going to be really great for you to use throughout the year. Hippocampus.org is a good website as well. It's got more videos, lessons from Khan Academy. It pulls in things from a lot of different resources, which is great. And then this last link, the PhET simulations, we will be using in class, so it's good to have bookmarked on your Chromebook. On the first day of school, again, we will be collecting this math and vector practice assignment, which is the packet itself. And we will be collecting the laboratory design assignment, which is going to be a separate one-page write-up of your lab design. Again, we'll talk about that at the end of the video. The most important thing as you're doing this packet is to try the best you can. No, you probably don't know everything, and that is okay, but you need to try. On the first day of class, it's really great for you to have a binder for this class, or like an A-Day, B-Day binder situation. You got some room for physics, and then also having a calculator. We do prefer the Texas Instrument models, but if you have a Casio already, that's totally fine, but you do need your own calculator for this class. It's going to really benefit you to have your own one, okay? So let's go ahead and dive into this packet. We're going to not go through every single problem, but I'll help you through some stuff. On page 3, we've got an equation sheet. This is an equation sheet that you will get a personal copy of that you'll be able to keep for the entire year. It says 2015, but it's still effective today. The main thing we're going to look at for this assignment is the unit symbols and the prefixes. Really just the prefixes, actually. But unit symbols will be helpful as we go through the year. And like I said, that prefixes box is going to be really helpful as we're looking at the first page of the actual assignment, okay? So as we look over to the right side on page 4, math and vector practice, it does say there that calculators should be avoided. Okay, that doesn't mean you can't use them, but we want to show your work and we want you to try to do it without a calculator as best as you can, okay? Mainly it's just math practice, but math is not the best thing for a lot of us. So I understand if you have to use a calculator, but try to show your work before using that calculator. First things up is scientific notation. Hopefully you have done some scientific notation before, or you've at least seen it. If not, don't panic, it's okay. Basically, scientific notation is a way of writing numbers where you've got a number times 10 to the something. So we've got first 5 times 10 to the negative 8, and then 2.9 times 10 to the 2. Okay, the first thing we're going to do is forget about those times 10, and we're just going to take 5 times 2.9. Okay, so if you forgot how to do some multiplication with decimals, it's pretty much the same as without decimals. Okay, so 5 times 9 is 45. We're going to put that decimal place in there. 5 times 2 is 10, plus 4 is 14. So 5 times 2.9 is 14.5, but we're not done. Now we have to take into account those times 10 to the okay? When we have exponents and we are multiplying them together, like we see here, when we're multiplying them, we add whatever the exponents are. So x squared times x cubed is 2 plus 3x to the 5th. Okay, so what we got here is 14.5 times 10 to the negative 8 plus 2. Negative 8 plus 2 is negative 6. So we've got 14.5 times 10 to the negative 6. Because negative 8 plus 2 is negative 6. However, this is not full scientific notation. In order to write a number in scientific notation, it has to be between 1 and 10. And this is a number that's greater than 10. So what we're going to do is we're going to move that decimal point so that we can actually make this number less than 10. So we're going to move the decimal point one space to the left. So it's going to become 1.45. And when we move decimal places to the left, we're creating a smaller number from a bigger number, so we're going to add 1 to the exponent. So it's going to be 1.45 times 10 to the negative 5th. Okay, if that was a lot for you, don't worry. There are a lot of good resources on the internet, especially Khan Academy, that talk about scientific notation. Give them a look. Just Google scientific notation multiplication, or how does scientific notation work. Okay, with number 2, it's kind of written weirdly. This 6 times 10 to the negative 11th is being multiplied by this fraction. And when we see fractions in physics, we mean division. Okay, so what you're going to do is the same process. Take those numbers out in front and then deal with your times 10 to the. So we've got times 10 to the negative 11th plus 26 minus 7. Okay, because when we divide things that are exponential, those exponents subtract. So like x to the 7th divided by x to the 4th is going to be x to the 3rd, because 7 minus 4 is 3. Okay, so you'll have some number times 10 to the negative 11 plus 26 minus 27. And you'll simplify it that way. Okay, moving on to number 3, unit conversions. For these unit conversions, we are looking at SI prefixes. Hey, prefixes, that sounds familiar. We're looking at the prefix table on the equation sheet. SI means like worldwide accepted prefixes. So everybody in the world uses these prefixes that is doing physics, okay? First thing, we're looking at the symbol. The symbol for the first row there is N. So what we're going to do is look on the table. N is nano. So we're going to write the name nano in the middle column, because that's the name of the prefix. And we're going to write the numerical equivalent 10 to the negative 9. Yes, that 10 to the negative 9 does mean scientific notation. That's why we started with scientific notation. Let's jump kind of towards the bottom of the table here. We've got K. K is kilo, looking at that prefix table. Okay, kilo is 10 to the 3rd. You have probably heard of kilometers before, right? Kilometers is a measure of distance. Instead of miles, kilometers, okay? So again, when we think about this in terms of scientific notation, kilo is 10 to the 3rd. So we have 10 to the 3rd meters. That's what a kilometer is. A kilometer is 10 to the 3rd meters. And 10 to the 3rd is 1,000. 10 times 10 is 100, times 10 is 1,000. So 1,000 meters is a kilometer. That's what these prefixes mean. They tell us how many of something we have. Do we have 100? Do we have 1,000? Do we have 10,000 of those things? Okay, so just using the table that is provided on the equation sheet to do the unit conversions. Numbers 4, 5, and 6 are actual converting of units, and hopefully you did a little bit of this in chemistry. Okay, so looking at that example, hopefully that maybe it doesn't make a whole lot of sense, but maybe it looks familiar. We're going to look at number 5. Basically, the setup is that you take whatever your first number is and you use unit conversions to get to the final unit that you're trying to get to. Okay, so for the example, there are 1,000 meters in a kilometer, there's 100 centimeters in a meter. And what you're doing is you're trying to cancel out whatever unit is on the top with the corresponding unit on the bottom. Okay, so in the second fraction, we've got kilometers on the bottom because that's the unit that we started with. And you go from one unit to the next unit to the next unit to the next unit. Okay, so we're going to look at number 5 here. 8.99 times 10 to the 9th seconds is how many years? We're not going to look at number 4 because it's pretty much the same setup as the first part of the example. And number 6 is kind of an extension of number 5. So we'll start with number 5. Like I said, 8.99 times 10 to the 9th seconds is how many years? Remember, positive exponent means a big, big number. So we've got lots of seconds to start with. Okay, so we're going to put that number over 1, and we're going to multiply it by the next unit. We're trying to get to bigger units here. Second is a very small unit. Years is a very big unit. Okay, so we're going to use the next unit up, which is a minute. There's 60 seconds in a minute. So we're trying to cancel out seconds, so we put seconds on the bottom. Then we multiply by the next unit up, is hours. There's 60 minutes in 1 hour. Again, minutes goes on the bottom because we're canceling it from the top of the previous fraction. Then we go to the next unit up. What's behind hours? It's days. Okay, so we've got 1 day is 24 hours. Whatever unit we're moving to, that's the unit that goes on the top. Whatever unit we're trying to get rid of, that's what goes on the bottom. Okay, 1 day is 24 hours, and the last unit, 1 year, that's what we're trying to get to, is 365 days. So as you are trying to find out how many seconds this is in years, you're taking these fractions and you're multiplying them by each other. So 8.99 times 10 to the 9th times 1 divided by 60 times 1 divided by 60 times 1 divided by 24 times 1 divided by 365. You can definitely use your calculator for these 3 problems. You have my permission. Okay? Especially for 4 and 6 as well. You notice there's some weird numbers in there. It's not going to be super easy. Okay, when we're looking at this scientific notation, I didn't talk about this earlier, but we can talk about it really quickly. 8.99 times 10 to the 9th, that exponent on your 10 tells you how many decimal places you need to move your decimal to the right or to the left. Okay, so remember that positive exponents mean that it's a really big number. That's how many spaces you're going to move it to the right because it's a big number. So you're moving the decimal place 9 times to the right, which means you've got 8.99 followed by 7 zeros. So we have 899 0 0 0 0 0 0 0. That is what 8.99 times 10 to the 9th is equal to in seconds. Okay, so take that number as your starting number and then follow with the fractions. So 899 0 0 0 0 0 0 0 times 1 divided by 60 times 1 divided by 60 times 1 divided by 24 times 1 divided by 365. Okay, number 4 is a little bit simpler. Number 6 is a little bit more challenging because you're moving from meters per second to kilometers per hour. So you're changing 2 units. That one's really tricky. Be patient. I believe in you. Moving on to the next page, trig review, trigonometry. I know how much we all love trigonometry. When we talk about trigonometry, really what we're talking about is SOHCAHTOA. We're talking about right triangles and properties of right triangles that are true for all right triangles. Okay, so sine, cosine, tangent, using opposite and hypotenuse and adjacent sides to be able to figure out angles. This little symbol down here, this is a Greek letter theta. It means angle. I'm not sure if everybody has seen that, but it's a stand-in for angle. In addition to SOHCAHTOA, when we're talking about trig, we also talk about the Pythagorean theorem, a squared plus b squared equals c squared, because that's true for all right angles. We are going to look at number 7 and number 9 here. Number 8 is similar to number 7. Number 10 is similar to number 9. Okay? So if we're starting to find c, given a and b, we're just going to use the Pythagorean theorem. We got a, b, and c. That's the only equation that has a, b, and c. So c squared equals a squared plus b squared. However, we want to find c by itself. We don't want to find c squared. So we're going to take the square root of both sides to get rid of that squared on our c, and we have c equals the square root of a squared plus b squared. Now, I know that this seems weird that this is an answer, but this is an answer because we don't have any numbers. We're just dealing with symbols, and that's as close to an answer as we're going to get. That's a perfectly good expression. In number 8, you're trying to find a if given b and c, so it's a little bit different, a little more rearranging that you'll have to do. And number 9 here, we're going to do, we're trying to find b if given a and our angle theta. So if we're looking at our triangle up here at the top, in reference to the angle, A is the opposite side and B is the adjacent side. So we're dealing with tangent, opposite and adjacent, that's tangent, TOA. So we're going to write out tangent of our angle, tangent theta, equals opposite is A over adjacent, which is B. Now we want to get b by itself on one side of the equation. Right now it is in the denominator, which we hate, and it is not by itself. So to get it out of the denominator, the first thing we're going to do is multiply both sides by b. Get it out of the denominator. Then we have b times tangent of our angle is equal to a, because the b's cancel on that side. We want to get b by itself, so we want to move tangent now over to the other side, tangent of our angle. So we're going to divide both sides by tangent of theta, and we're left with b equals a divided by tangent theta. In physics, when we write our division signs, we always write them as fractions. Okay, we don't write the division symbol. We never do that. We write them as fractions. Okay? In number 10, you're trying to find theta, find the angle if given b and c, so you got to think about which trig function that is. Is that sine, cosine, or tangent? And then do a little bit of extra stuff. Okay? Moving on to number 11. Again, I know that this is kind of fast and furious, but this is just an overview. If you have more questions, please ask. Please email me or Mr. Andringa. All right? Number 11 says, using the properties of triangles, prove that angle A is equal to angle C in the drawing below. We are going to use some properties of triangles here. Okay, you'll notice that there are multiple triangles in this drawing. We've got the big one, the red one, which we'll start with. I also labeled all of the other angles that weren't right angles here. I labeled them D and E. Okay, so looking at the big triangle, we're going to look at the 3 angles in the big triangle, A, E, and this right angle. We know that all angles in a triangle have to add up to 180 degrees. That right angle is 90 degrees, and whatever A is and whatever E is, all of those have to be 180. So we got 90 plus A plus E equals 180. So that means that A plus E has to equal 90 degrees. Because we can move that 90 degrees over to their side. Next, we're going to look at this wonky little triangle here. Same thing, all the angles add up to 180, the 90 degree angle plus C plus D, which means that C plus D equals 90. Then we're going to look at this smaller triangle on the right hand side, this green triangle, same thing. A plus B now has to equal 90 degrees. And I want you to draw your attention here to the top in red. A plus E equals 90 degrees, and then in the green, A plus B equals 90 degrees. That means that B and E have to be the same angle. We're not trying to prove that, but it's something to point out. Okay, we also know that they are like mirrored to each other in the drawing. So it makes sense that they're the same angle. The last property of triangles that we're going to consider here is what's happening at the angle of B and C. Okay, so we know that B plus C plus that right angle has to be 180 degrees because it's a flat line. So then we know that C plus B equals 90 degrees. But hold on, A plus B equals 90 degrees. C plus B equals 90 degrees. That means that A has to equal C, right? Let's say B is 45 degrees. It's not, but let's say it is. Then A plus 45 is 90. C plus 45 is 90. That means that they have to be equal. Okay? So in your own work, I want you to write a little bit more as to how we made that jump to know that A equals C. Provide a little bit more explanation there. Moving on, what is the area under the curve? Number 12. I know this is a really weird question. what we're looking at is a graph, and you might see a shape. There is a shape in this graph. When we talk about area under the curve, we're talking about the area that is formed between whatever the graph is doing, so this flat line and then declining line, and between the axes themselves, so the y and the x-axis. What are we looking at here? A trapezoid. We want to find the area of this trapezoid. And something to make it easier for ourselves, we can split it into two different shapes if you can't remember how to find the area of a trapezoid. We can split it into a triangle here and a rectangle there. So hopefully you remember how to find the area of a rectangle. We're just going to find the area of both of these shapes and add it up, assuming that those two axes are 0. Then our rectangle has area of 4 by 12. And then our triangle also has a height of 4. It's the same height as a rectangle. And it has a base, let's see, from 12 to 20, that's 8. Goes from 12 to 20, there's 8 spaces there. Remember that the area of a triangle is equal to 1/2 base times height, or base times height divided by 2. Either way, you're going to find the area of the rectangle, find the area of the triangle, and you'll add them up, and that's the area under the curve. Moving on to the next page. We've got some algebra review, and you might look at this page and be like, this is not algebra. It is. It's just different. There's less numbers. Okay, so there's an example that is given to you where you want to solve for x. And I know that there's also y and there's also z. It's okay. It's okay. We are going to look at number 13 and number 15 together. Okay, number 14 is similar to number 13. 16 and 17 are a little bit trickier, but it's going to be okay. We're going to do 13 and 15. Again, even though there's no numbers, it's okay. When we say solve for something, we just mean rearrange the equation so that that something is by itself on one side. For example, in number 13, we're solving for VI. VI is not by itself on one side of the equation right now, so we want to get it by itself. So we're going to rewrite the equation here. VF squared equals VI squared plus 2AD. Now, these numbers and these equations mean nothing to you. These letters mean nothing to you, and that's okay. All right? First thing we got to do to get VI by itself, we want to move that second term, the 2AD, over to the other side. Right now it's added to the right side. We're going to subtract it over to the left side. Cancels there on the right. So we have VF squared minus 2AD is equal to VI squared. Just like with what we saw with the Pythagorean theorem, okay, this is not our final answer. We want VI by itself. Right now it's being squared. We want to get rid of the square by square rooting both sides. So that squared cancels out, and we have VI equals square root of VF squared minus 2AD. Again, I know this is weird that there's no numbers, but we're going to be doing this all the time. All the time. It's really important that we at least try right now. Okay? Embrace the fact that there's no numbers and we're just moving letters around. It's going to be okay. Part B, now we're solving for D. So a little bit similar, a little bit different. Okay, same equation, VF squared equals VI squared plus 2AD. Now, we're going to leave the 2AD there. We're going to move our VI term over to the other side. So we're going to subtract it. Subtract VI squared from both sides, because right now it's being added to that 2AD. We want to subtract it over to the other side. Now we've got VF squared minus VI squared equals 2 times A times D. 2AD. So those are all being multiplied by each other. 2 times A times D. So in order to get D by itself, we want to divide by 2 and A at the same time. Yes, we can do that. It's legal. Okay, so they cancel there on the right side. We're left with D equals VF squared minus VI squared divided by 2A. Again, when we're dividing in physics, we never write the division symbol. We only write it as a fraction. We never use the division symbol. Never. This is how it is, as a fraction. Because fraction means division. Okay? Number 14 is kind of similar to number 13. We're going to jump to number 15. Okay, we'll kind of come back and talk a little bit about 14 here in a second. Looking at number 15, we have AC equals V squared divided by R. And we want to solve for V. Okay, so we're going to basically, this one's pretty simple actually. We're going to move the R over to the other side, get it out of the denominator, multiply both sides by R. It cancels on the right. We're left with R times AC equals V squared, just like we saw with the Pythagorean theorem. We're going to square root both sides. We've got V equals the square root of R times AC. Again, take a moment, maybe pause the video. If this is a lot, I know it's weird. It's going to be okay, I promise. All right, I know it's weird with all the letters. Number 14, number 16, and number 17, they all have a little extra to them. So if we're looking at number 16, it says solve for HF if HI is 0 and VF is 0. 14 has the same thing in part B, solve for T if V0 equals 0. What that tells you is that before you solve for anything, before you move anything around in your equation, you're going to plug that 0 into the equation. So looking at 14, if we plug in 0 for V0, well, 0 times anything is 0, so that whole term drops out, which is amazing. We don't have to worry about that anymore, because 0 times t, no matter what t is, 0 times anything is 0. So it drops out. So we're left with df equals di plus 1/2 at squared. It makes it easier to solve because one of the terms is gone. Same thing with number 16. You're going to plug in those zeros first and see how that changes your equation, what it gets rid of. Number 18 is the last part of the algebra rearranging. Numbers 19 and 20 we are not going to go through. Hopefully you know how to add fractions without using a calculator. It's okay if you don't remember, but take some time, relearn that skill. We're going to jump to number 21. Number 21 is all about relationships. If we change one thing, how does the other thing change? We're going to go through A, we're going to go through D, we're going to go through, let's see, G, and I. Okay? So we'll do one of each of those equations. Now, again, we're just dealing with symbols. We're not doing numbers, so we got to think more conceptually here. Okay? Starting with A, as x increases and y stays constant, z does what? Okay, well, we've got a fraction here. If the numerator of the fraction goes up and the denominator doesn't change, let's say the denominator is 1. Let's say x is 2 and we raise it to 3. 2 divided by 1 and then 3 divided by 1. Well, we increased x, that means that z is going to increase as well. If you increase the numerator of a fraction, you're increasing the overall number. Okay? So as x increases, z is going to increase. It's not the same with b and c. You've got to think how the denominator changes and how that changes the overall number. Moving on to D. As a increases and c stays constant, what does b do? A little bit of a different equation here. C equals a times b. As a increases, c stays constant. What happens to b? Okay, so if whatever our number is for c, it's staying constant, it's 1. Okay, we increase a. Well, if we're multiplying two numbers together and we increase one of them, but we want the overall number to stay the same, we have to decrease the other one. That's what's called an inverse relationship. So if a increases, but we can't change our overall number, that means that b has to decrease. Moving on to G, as n increases and m stays constant, what happens to L? L is equal to m minus n. N is the thing that's increasing. We're subtracting a bigger number, which is going to decrease our overall number, our result. Okay, so if m stays the same, m is 1, and we are subtracting a bigger number from 1, we're going to decrease our result. Finally, I, if s is tripled and t stays constant, r is multiplied by what? Okay, so this is a little bit of a different format here. We've got some squareds, and instead of saying is it increasing, is it decreasing, we want to know how it's changing. So s is tripled, that means s is times 3, but s is being squared. So if s is tripled, That means it's not just s squared anymore, it's 3s squared. And when we have that exponent, we have to distribute to both terms. The squared goes to the 3 and the squared goes to the s. And what's 3 squared? 9. So r is going to be multiplied by 9. Because if s is tripled, well, r is affected by that squared on the s. So it's not just multiplied by 3, it's multiplied by 9. J is kind of similar there. It's going to be a little bit different. Okay? Moving on to vectors. Vector! Oh yeah! If you have seen Despicable Me, yes, the villain in Despicable Me is mathematically correct. Remember, he says, I'm committing crimes with direction and magnitude. Oh yeah! He's right. That's what a vector is. It has magnitude and direction. Most things in life are scalars. How many fingers do you have on one hand? 5. That's a scalar. Okay, it just has an amount. A vector has an amount and a direction. So you're driving 30 miles an hour north. Something about that quantity also has an attached direction. You're backing out of the driveway. You're moving backwards. Okay, you run a 5K to the northeast. Okay, you slide to the left, slide to the right. Those are vectors. Okay, magnitude and direction. Magnitude means how much speed do you have? And then the vector part of it is the direction. Which way? How much? Which way? Okay, so please read this. Please read this a couple times, this passage here about vectors. Okay, negative vectors just means a flipped direction. Okay, so if I said I was going negative 30 miles an hour, I'd be going 30 miles an hour south. Okay, if we think about the coordinates in math, coordinate system, x and y axes, and we think about north, south, east, west, that means north and east are positive directions, south and west are negative directions. We will continue to talk about this in physics, but it's just something to talk about right now. That means the positive vector would be 30 miles an hour north, but if I said, oh, it's the negative vector of that, it's just the opposite direction, 30 miles an hour south. This is a really, really important statement here on the bottom of the page. A negative number does not mean a smaller number. Just let that settle for a second. A negative number doesn't mean a smaller number. If you're thinking about a number line in math, then yes. Okay, you would say that negative 2 is less than positive 2. However, a negative number does not mean a smaller number in physics. It just means you're going the opposite direction. Instead of taking positive 2 steps and going forward, you took negative 2 steps and went backwards. You had the same amount of steps. The same magnitude, the same muchness was the same. Okay, but it's just the direction that changes. Instead of walking 3 steps to the right, you went 3 steps to the left. Positive 3, negative 3. Okay, so with our example up there, 30 miles an hour north, 30 miles an hour south, those are negative vectors of one another. Negative 30 miles an hour north is 30 miles an hour south. Okay? When we talk about vectors, usually we have to talk about adding vectors. So you walk from the high school, let's say you go across the street to get some pizza, and then you just jaywalk across the intersection to get to the tennis courts, let's say. Okay, so you want to eat your lunch by the tennis courts. Not sure why, but that's what you do. Okay, so you walked to the right, and then you walked down and to the left, or you walked east and then southwest. Overall, though, your trip from the high school, if you just talked about start to finish, you went from the high school south. That's your result, capital R. Your resultant vector was from the high school to the tennis courts, you walked south. So this happens a lot in physics where we've got 2 different vectors, 2 different directions, and we have to add them to figure out where we ended up. This parallelogram method is not my favorite. Usually, all the time in class, we'll be doing the tip-to-tail method. Okay? Tip-to-tail is really easy where you just add on the vector where the previous vector ended, and then you go from start to finish. Okay? For minus, remember minus means the opposite direction. So right now we're looking at positive b, so we just flip the direction and it makes negative b. Might be helpful to have kind of a straight edge or a ruler for these 2 pages. My lines are not very straight, but that's okay. Okay, so using the parallelogram method is number 22. There's a couple different parts there for you. Okay, basically you're just completing the square, completing the rectangle, completing the parallelogram, if you will. So you're putting the that downward facing vector, putting it on the other side, and then that leftward facing vector, putting it on the other side, and where the 2 vectors meet, that's your ending point, and you draw a line from your start to your end. Okay, let's do it with A as well. So we're going to draw that northeastern vector, we're going to draw it on the other side, and then we're going to draw that eastern vector to complete the parallelogram. That's our ending point where the 2 vectors meet, and then from start to finish is our resultant vector. Okay, that R means resultant, which means from start to finish. Okay, as I said before, we do prefer the tip to tail method, which is on the next page, number 23, where you just take one vector and you add the next vector directly onto it. Okay, so looking at B, right now we have positive S, we want T minus S. So T still points up and a little to the left, but minus S, instead of pointing to the left, it's going to point to the right. So T minus S, we add S onto where T ends, and we go from start to finish. That's our resultant vector. You could get it going the parallelogram method too. I feel like the parallelogram method takes longer. Be careful with D on number 23. There's 3 vectors there, and they're all negative. Be careful. We are finally wrapping up here. Direction. What does direction mean? It means like with reference to what. Okay, so like forward with reference to what. Okay, like I talked about before, the coordinate system in math is kind of our go-to for how to pick positive and negative directions. Positive Y up, negative Y down, and so on and so forth. Okay, on this very last page, we are talking about component vectors. Every vector is made up of one vector that has an up portion, one vector that has a down portion, one vector that has a right or to the left. Okay, we want to go back to those basic coordinate axes. So this one that we're looking at here in the example, it's pointing to the right and it's pointing up. So we have a component that points to the right, we have a component that points up. Our x component points to the right, our y component points up. Okay, so for number 24, draw the following vectors, draw the following component vectors along the x and y axes. So for A, that vector points to the left and it points up. So there's a component that points to the left, that's our x component, and there's a component that points up, which is our y component. And the one that's already there is our resultant. You can label them x and y, you can label them rx, ry. Okay, that one that points to the left, that's negative, left is negative, so that should be a negative x. And then for B, that resultant is pointing way up, a little bit to the right, so we have a little arrow to the right, we have a big arrow up. X component, y component. Okay? Finally, looking at laboratory design. Up to 1 hour, don't spend a million years on this. Okay, you're going to design an experiment to explore the relationship between mass of an object and the time it takes the object to drop from a height. Do you think heavier things fall faster? That's what we're asking you here. Okay? Basically, what you're going to do is list any common accessible lab equipment needed, outline a procedure for data collection, and include a labeled diagram of the setup. I said basically, it's not super basic. I know that probably sounds really daunting to you. I want you to take a look at the space that you're in right now. I want you to find 4 or 5 different objects that you think have different mass. Okay, so maybe you've got your AirPod case. That's pretty light. You've got your phone, a little bit heavier. Maybe you've got a water bottle. Okay, maybe you've got a blanket, and maybe you have the notebook that you're working on the lab design project in. Okay, so you got 5 different things, and I want you to make a prediction in your head which one is going to fall the fastest. Okay, How would you put that to the test? First of all, if you're going to time the time it takes to make something drop from a height, well, first of all, what height? Are you going to drop it from your desk height, from higher, from up to the ceiling? How do you measure that height? What do you need to measure that height? A meter stick. Yeah, okay? Also, how are you going to time something? What do you need to be able to time the time it takes an object to drop? You need a stopwatch. How are you going to find the mass of each of these objects? You need a scale. Boom, I just gave you the lab equipment you need. Procedure, how are you going to proceed with this lab? You're going to drop all of them at once? No, you're going to drop each one at a time and time the time it takes to hit the ground. Okay, are you going to time it once? Are you going to time it twice? 3 times? You're going to take the average of the times? What are you going to do? Okay, and then draw us a picture. What does your setup look like? Okay, so like take a page. Take a page, doesn't have to be like push notes all super small and together. Doesn't have to be super pretty. Okay, but tell us, what do you need? What are the lab equipment? What's the procedure? And then show us a diagram. Okay? Like I said at the very beginning, if you have questions still, please let me or Mr. Hendriga know. Send us an email. However other method you have of reaching out to us, I'm on Instagram and TikTok. Okay, send me a DM if you've got questions. We are so excited to meet you all on the first day of school and to go through AP Physics together. Also, I said at the beginning, and I'll say it again, you do not have to know all of these things already in this packet. It's just to get your mind braining a little bit. Okay, get the mathing, and then we'll work on it together. We'll answer your questions. We'll practice these skills all year long. Okay, we're super excited to meet you. Super excited to get started with physics. Good luck with the rest of this packet. Please let us know if you have more questions, and enjoy the rest of your summer.